No? Okay, so let's just do the chain condition first. So this is a technical kind of thing. If you're more of a set theory person, you're familiar with the phrase chain condition because you learn things like the countable chain condition or the all of 6 chain condition or whatever. And that's not just a coincidence. In fact, Shalad uses this property to prove that a certain forcing notion has a certain chain condition, although the exact one is very complicated to state. And he proves that, okay, if you have some esoteric forcing axiom, which is like a variant of Martin's axiom in place, then you can saturate simple theories without saturating non-simple theories, certain precise way. So this chain condition is actually explicitly related to a certain forcing notion, which we won't go into, but that's where the name comes from. So what does the statement say? So let's write it, proposition. Suppose T is simple. Then if A is independent over A with B0, and I, Bi less than omega is an A indiscernible sequence, then there exists some A prime, which is the same type as A over AB0, such that, okay, two things happen. One is that our sequence I is A prime indiscernible. So you upgrade the indiscernibility. Let me, indiscernible. But that you would get just from knowing that A was independent from B0. If you knew that A was independent from B0, then by non-dividing, you know that you can move A to A prime such that you upgrade the indiscernibility. The real new thing is that you get that A prime is independent with the whole sequence over I. Okay, so the first bit just comes from independence. The second bit is new. So let's recall how we started. So without loss of generality, we can stretch I. Well, it's not really without loss of generality. Let's just say we can stretch I to I is equal to Bi I less than omega plus omega. So we make it twice as long. So let's draw a picture. We've got the first omega and the second omega. And I don't know, here's B0 and here's B omega. And we had some relations that held between A and B0, like that. So what we're going to do first is we're going to pick some A prime such that it also relates to B omega in the same way. And we can do that because B0 and B omega have the same type over A, because they're on an indiscernible sequence. So I can copy the relations that hold between A and B0 to some element A prime, which holds not between A and B0, but A prime and B omega. So pick A prime such that A prime is independent, or no, sorry. A prime B omega has the same type over A with A B0. And this is possible because the BIs live on an indiscernible sequence. So in particular, they all have the same type over A. Okay, so that's the first step. So by invariance, it follows that A prime is independent over A with B omega. If A was independent with B0 over A, and A prime B omega have the same type as A B0 over A, then it follows that A prime is independent with B omega over A, because independence is invariant under automorphisms. So by extension, there is A prime prime, which has the same type as A prime over B omega, such that A prime prime is independent, not just with B omega, but actually with B less than or equal to omega. So extension says that if you add more parameters, you can move the object to be independent, not just with the old parameters, but also with the new ones. preserving the type. So now we've made it independent, not just with b omega, but in fact, you're independent now with this whole initial segment up to and including omega. So by base monotonicity, A prime prime is independent over F, or sorry, independent over A B less than omega with B omega. So all we did was we moved something from the right into the base. And that means that, we've made a weaker statement. So this is certainly true. Now, last time we saw that if I look at B omega plus I less than omega, this is a Morley sequence over A B less than omega indexed in reverse. Okay, why? Well, if we go back, sorry, I don't want to, those of you that are taking notes, I don't want to somehow make it possible to see what it says while also looking at the picture. So here's what I'll do. I will copy this very quickly. Okay, duplicate, and we'll move this down. Oops. Okay, so let's look at this picture. So let's get rid of these bits for a moment. The main thing was just that if you take a formula which, say, uses parameters here and parameters here, and which is satisfied by b omega, so if it's satisfied by b omega, then it has to be satisfied by any sufficiently large bn, because it's indiscernible. So if it's satisfied by b omega, then it's also satisfied by an n segment of elements of the bi's for I less than omega. Just by indiscernibility, I can slide down. So that means that the type of b omega over everything above it and everything below it is finitely satisfiable in the stuff below it. And finite satisfiability implies that b omega is non-forking independent with the stuff above it. So by indiscernibility, I can conclude that b omega plus I is independent with b omega plus j for j bigger than I for every I. And that means that it's Morley in reverse. So we have this argument where we showed, okay, we have a certain amount of finite satisfiability that comes from indiscernibility that implies independence. Okay, so by the chain condition for Morley sequences, there is A prime prime prime. I think we already have two primes, yeah? Yeah, A prime prime prime, which has the same type over A b less than or equal to omega as A prime prime, such that B omega, okay, I'm just going to write it B greater than or equal to omega, which is our Morley sequence, is A prime prime prime, B less than or equal to omega, or sorry, B less than omega in indiscernible. Okay, let's recall what the base was. The base was AB less than omega. So I have the base plus the object. So that's A prime prime prime, and B less than omega indiscernible, and A prime 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 is independent over A with, sorry, AB less than omega with all of B greater than or equal to omega. So the chain condition says if I have A independent with B and you give me an indiscernible sequence starting with B, I can move A to A prime such that I've upgraded the indiscernibility. So I'm indiscernible not just over A, but with A prime, and A prime is independent with the whole sequence. So that statement is something we proved last time when we assumed the sequence was additionally a Morley sequence. So over A b less than omega, we know that this tail segment of our indiscernible sequence is a Morley sequence over this bigger base. So we can apply the chain condition, this weaker chain condition, which is just for Morley sequences here. And that means we can make this indiscernible and independent. Okay, so then by base monotonicity, again, we have A prime 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 is independent over A B less than or equal to omega, B greater than or equal to omega. I just moved the omega bit into the base. So now, since we know, let's remember how we picked A prime prime prime. We have this condition here. So since we know that A prime 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 has the same type over A B less than or equal to omega as A prime prime, and A prime prime was taken to be independent over A B less than omega with over A with B less than or equal to omega, we know, so I just put an F there, we know also A prime 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 is independent with B less than or equal to omega. So how did we pick A prime prime? We picked A prime prime to be independent over A with B less than or equal to omega. That is what we have here. So this was how we chose A prime prime. So it was independent with B less than or equal to omega. So because we preserve the type, we also have that here. Then together with A prime 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 independent over F with B greater than or equal to omega over B less than or equal to omega, we have A prime 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 independent over A with all of I by transitivity. So what this is saying is that if I go from A to B less than or equal to omega, that's a non-forking extension. That's this first bit. And if I go from A, B less than or equal to omega to A, B less than or equal to omega together with B greater than or equal to omega, that's also a non-forking extension. And what transitivity tells you is that a non-forking extension of a non-forking extension is a non-forking extension. So the move from A to the whole thing is also non-forking, and that's exactly what we wanted. Okay, so what I was missing last time is this fact here, that we knew that we were independent with the initial segment also by extension. And I somehow my mind was just not remembering this fact. But once you have that, then it's just easy application of transitivity. Okay, so that's the proof. And you know, I'm still a bit traumatized by forgetting it last time. So I'm, you know, I'll try to make it up to you by giving only correct proofs from now on. All right, so now we want to move on to the independence theorem. And this, I would say, is like the hardest theorem of pure simplicity theory. And it's a pretty big deal. I mean, I think if we had maybe like 2 more weeks, I would spend 2 more weeks just doing simple theories, and you'd get to see all the fun applications of this fact, which seems very innocuous. But the independence theorem says the following thing. It says, suppose T is simple. You have A, which is the same type over M as A0. You have B, which is independent over, over M. I should say that M is a model. So there's a more general statement that you can say over sets, but it's hard enough over models, so we'll restrict to that case. So you have B independent with C. A0 is independent with B. A1 is independent with C. And that's it. So then there is A star, which has the same type over MB as A0. It has the same type over MC as A1. And A star is independent over M with both B and C. So the picture is you've got some
Nick,
model.
what's the first condition?
Which one? A0 equivalent to M1? Or sorry, A0. Oh, that's true, but not interesting. It should say A1. Thank you. Yeah, it is true what I wrote, but not interesting. Well, I mean, the conclusion is not true just from that hypothesis. So thank you. Okay, so you've got B here and you've got C here, and these are independent over M. And you've got A0 here, and you've got A1 here. And what you want to do is you want to amalgamate these. So you have some relations that hold between this bit and some relations that hold between this bit. And what you want is you want to somehow have something that combines these relations with these relations in an independent way. So it's not even obvious that such a thing should be consistent, right? Like if you have a larger set of parameters and you extend your type in two ways over this larger set of parameters, there's no reason that these should be compatible. So, for example, in a dense linear order, suppose you have a type over a model which says I'm in a certain cut. Then you look at a bigger set of parameters where you have a whole bunch of new elements inside this cut. One of the types could say I'm less than this new element, and another one could say I'm bigger than this new element. And those are just never compatible. You can't satisfy both. So how do you know that you can put them together? In the simple context, the idea is everything that isn't uniquely determined by being generic, like a stable theory, is random. So as long as things are independent, they can't place constraints on each other, and so you can put them together. This is like the guiding philosophy. And so this is what we will prove. All right, is the statement clear? Does everyone follow? Okay, so let's do the proof. And I guess this will take the rest of the time. So so what we'll do is we will let Px b be the type of A0 over MB, and Q xc will be the type of A1 over MC. So we want to show what? We want to show that the union of these two types is non-forking over M. Now, of course, an inconsistent formula forks. So part of being non-forking is being consistent. So we want to show that first it's consistent, we can realize it, but additionally, we can choose a realization which doesn't fork with B or C. So that's the goal. So to start, we will pick C prime such that A0 C prime has the same type over M as A1 C. So we've got our model, we've got B, we've got C, we've got A0, and we've got A1. And of course, like I had before, we've got some relations that hold between A1 and C, and we've got some relations that hold between A0 and B. And what we're doing is we're just going to pick some C prime that looks the same with respect to A0 as A1 looks with respect to C. And this we can do just using an automorphism, right? There's an automorphism over M that takes A1 to A0, see where it sends C, and then that's going to be your C prime. So that's the way you start. And we can apply extension to find C prime prime, which has the same type over M A0 as C, such that C prime prime is independent not just with A0, but also with B. Okay, so let's ask ourselves why this is possible. Or why possible? Well, what do you know? You know that A1 is independent with, sorry, I wrote A, but that's just out of habit. I really meant M. Right? So one of our hypotheses was that A1 was independent with C. So that certainly implies that A0 is independent over M with C prime, because independence is invariant. And that implies that C prime is independent over F with A0 over M by symmetry. So this is symmetry, which we proved. And that implies that there exists a C prime with the same type over M A0 as, sorry, C prime prime, with C prime prime independent over M with A0B by extension. So we're using the fact that we knew that A1 was independent with C and symmetry in order to get this point. Okay, so let's go back to our picture. So now we've chosen some other C prime, sorry, which looks the same, but notice now is very far away from B. It has no relations with B. All right, so now let's do some more forking calculus. So base monotonicity implies that C prime prime is independent over M with also B in the base, A0. I just moved B from the right side into the base. And by symmetry, B is independent with A0 over M. One of our hypotheses was that A0 is independent with B, so of course I can switch the order. So what does this look like? This looks like transitivity. So by left transitivity, I have B C prime prime is independent over M with A0. Hence, A0 is independent over M with B C prime prime by symmetry. So maybe it's worth pausing for a moment and just reflect on how magical the non-forking calculus is. Because if you have to think about, okay, what happens if I write down a formula that divides and blah, 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 it's a huge mess to think about the kind of moving around elements and arranging for things to be independent and seeing which implications obtain between different kinds of independence that happen between different tuples. So what is amazing about simple theories is that you have a kind of like formal calculus. You develop some properties of the independence relation, and the proofs of those take some work. You have to develop some theory using like Kim's lemma and whatnot. But then once you have it, you just use it formally without thinking about what it means. You don't have to think about formulas or indiscernible sequences for most of what you do. And so that's really why this is like a useful theory. You know, like when you're analyzing a structure, you don't want to have to keep thinking about what arbitrary formulas look like, what indiscernible sequences look like. You just want to sort of set up the independence and then use it. And simple theories are a context in which you can. And that's one of the nicer features of this setting. Okay, so our conclusion is here that if I look at Px B union Qx C prime prime, this does not fork. Over M. Why? Well, because this is realized by A0. A0 realizes this. Why? Well, because A0 has the same type as over MB as A0 did. That's not saying anything interesting. But also we chose C prime prime so that the type of A0 C prime prime is the same as the type of A1 C. I just replaced the parameter. So certainly A0 realizes both of these types, but also all this forking calculus that we did showed us that A0 was independent with BC prime prime. So I have a realization of this union of types, which is independent from the parameters, which means that that union of types can't fork. What does it mean to be independent? It just means that you don't fork. Okay, cool. So this tells us that we've got something interesting happening. So we had B and C, and we looked at the union of these two types, and we said, we want to show that that doesn't fork. What we did was we found some other C prime, which looks a lot like C, and we knew that the union of those two things doesn't fork. And what we're going to do now is we're going to say, okay, let's suppose that with C it forks and with C prime it doesn't fork. Then we're going to show that something breaks. Okay, and this is where, I mean, up to now it's just forking calculus. We haven't really done anything really shocking. We've just sort of used the properties of the calculus. Now we're going to do something which is a bit, I don't know that it's shocking, but it's a bit surprising, even to me. I mean, I think having thought about this theorem for many years, it still surprises me that the proof goes the way it does. So so what we're going to do now is suppose towards contradiction. That P x B union Q x C prime prime forks over M. This is the thing that we wanted to show doesn't happen. And so we're going to assume it, and we're going to violate the chain condition. This is why we worried about proving the chain condition to begin with. So fix some ultrafilter D on our model, on our model M to the length of C, such that the type of C over M is the same thing as the average type of D over M. So we proved before that if you have a type over a model, it is always the average of some ultrafilter on the model, because types in models are finitely satisfiable. So you can look at the formulas in the type that forms a filter, complete it to some ultrafilter, and then using that ultrafilter to tell you which formulas to put in the type gives you the type back. This is how we proved before that like every type over a model has a global finitely satisfiable and hence invariant extension. This is something we did maybe for a second week. All right, but this is also equal to the type of C prime prime over M, because these are the same type. C and C prime prime had the same type over M. By the way, this is where we use that the base is a model, because it's not true in general that types over sets are finitely satisfiable in the set, but that is true over models. So of course, if you wanted to do this proof over arbitrary sets, you would have to find a way of getting rid of this tool. You'd have to do it in a different way. And there are different ways of doing it, but this is where we use that hypothesis. Okay, so now what we're going to do is we're going to let Ci, I less than omega, be a Morley sequence in this global finitely satisfiable type over M, starting with C0. We're starting with C, sorry. So what do I mean? I just mean that, like, you know that C0 realizes the average of D over M, and then you choose some C1 to realize the average of D over MC0, and C2 will realize the average of D over MC0, C1, and so on and so forth, right? This is what we call a Morley sequence in a finitely satisfiable type. You just realize it inductively over the previous ones. And so you know that Ci, I less than omega, is M indiscernible. Okay. Now, let's see. What do we do next? Next, let C, what did I call it? C prime or C prime prime? C prime prime. Okay. Let C prime prime, I less than omega, be a Morley sequence in av d blackboard bold M over M with C prime prime 0 equals C prime prime. So we do the same thing now, starting with our other sequence. And we can do this because both of these elements have the same type over M. So I can, I can C prime prime can be my first realization, and then I realize it over that element, then I realize it over those two, and I realize it over those three, and that gives me another sequence. So also C prime prime I less than omega, is M indiscernible. Okay, and now we're going to do something bonkers, which is we're going to let di, I less than omega, be chosen so that, okay, you're going to choose d0 to realize average d over C less than omega, C prime prime less than omega over that whole sequence, both sequences. And D1 is going to realize the average type over C less than omega, C prime prime less than omega, D0. And D2 is going to realize the average type of D over C less than omega, C prime prime less than omega, D0, D1, and so on and so forth. So di, I less than omega, is a Morley sequence in the average type of D M over not just M, but over everything that we've done so far. Okay, so let's pause for a moment and just look at a picture of this. So again, we've got our model, M, and we've got our B out here, and we've got our A0 here, and then we've got our two C's. We've got C prime prime, and we've got C. And what we did was we took two sequences, like this, both in the same type, both in the same average type over M. But then what we did was, oh, whoops, that was farther down than I wanted to go. Then what we did was we sort of continued over both. So this is like D0, D1, D2, D3, and so on and so forth. So what's interesting is that we have both of these sequences are indiscernible. So both Ci, I less than omega, concatenated with Di, I less than omega, and C prime prime I less than omega, concatenated with Di, I less than omega, are Morley sequences of order type omega plus omega in this average type of D M over M. So what does it mean to have a Morley sequence, right? In a global invariant type or a finitely satisfiable type, you realize it, and then you realize it again over the previous realization, and you realize it again over the previous realization, and you just continue this. And you continue this transfinitely if you like. At limit ordinals, you can still realize it over everything that came before. So what happens if you do this omega plus omega many steps? Like you could start at C0, then C1, then C2, then C3, then C4, and then after that you could do D0, D1, D2, D3, D4. That gives you a Morley sequence of order type omega plus omega in this type. Or alternatively, you could go C prime prime 0, C prime prime 1, C prime prime 2, all the way through omega, and then go D0, D1, D2, D3, D4. And that gives you a different Morley sequence in the same type. So this is quite strange. You've got these two indiscernible sequences, and then they have a common tail. And that common tail is what we're going to sort of push against in getting a contradiction. All right, so what do we do now? So in particular, both of these sequences are MB indiscernible. Or sorry, M indiscernible. M indiscernible. We proved before that if you generate a sequence in this way, it's automatically indiscernible, which is an exercise just using the definition of invariance. Okay, so now by Ramsey compactness and automorphism, we may assume that di, I less than omega, is MB indiscernible. So what do I mean by this? Like just extract something which is MB indiscernible from it by applying the theorems that we did before. Like, look at its EM type over MB, realize that will still realize the same complete type over the stuff before. I mean, if you can make it indiscernible over the previous stuff, so like M, C less than omega, C prime prime less than omega, and B, and then it will realize the same type because it's already indiscernible over that earlier stuff. So without loss of generality, you can assume it's indiscernible over MB just by extraction, as we've done many times in this class. Okay, so now we're going to break up into cases. So case one is, what is case one? It's for some equivalently all I less than omega Pxb union Qx di forks over M. So what do I mean here? Here we've got M, we've got B, we've got our two sequences. And here we've got D0. And what we're wondering is, what is sort of the tail behavior? What's going to happen here? So I can look at this type Q x D0, and I can look at this type P x B, and I could say, okay, is the union of these two types going to fork or not? Those are our two cases. So either it forks or it doesn't. Case one is going to be that it forks, and case two is going to be that it doesn't fork. It has to do one of the two. And either way, we're going to be able to obtain a contradiction. So where is our contradiction going to come from? It's going to come from cooking up an indiscernible sequence that violates the chain condition. So here we do a construction which is kind of strange. So pick for each I less than omega some bi such that C less than I, B, D greater than or equal to 0 has the same type over M as D less than I, Bi, D greater than or equal to I. So this requires maybe a picture. So we've got an indiscernible sequence of order type omega plus omega. So here we've got the CIs, and here we've got the DIs, and here we've got B. So let's suppose, oh goodness. So let's suppose we're looking at a particular I. Shelby, please don't. All right, so I'm going to have two different kinds of relations happening. So let's say I have these blue relations happening between B and the C less than I. And I'm going to have like the red relations happening with the D's. Something like that. All right, but what we know is that this whole sequence, the CIs followed by the DIs, is M indiscernible. So in particular, if I look at the first I C's and then all of the D's, that has the same type as the first I D's and then the rest of the D's. That's still something of order type omega, and it's like a subsequence of the sequence. So it's got to have the same type. So as a consequence, what I can do is I can pick some other thing, which I'm going to call BI, which relates to the sequence in the following way. For the first IDs, for the first IDs, I relate like this. And then for the last Ds, I relate like this. Does that make sense? So I'm just sort of copying. And I can do this because of indiscernibility. So that's how I pick my BIs. All right. So note, oh, let me switch back to black. Note that for I greater than or equal to j, we have bi dj has the same type over M as C prime j b, which has the same type over M as C prime b by the choice. And oh, I should have made a comment here, which is right. Sorry. So okay. Comment should have assumed. So when I took the sequence at the beginning, I should have used that B is independent with C over M to assume that the sequence C I less than omega is MB indiscernible. So I forgot to use this hypothesis, and this is where we use it. So when I chose the sequence of C's, that's an M indiscernible sequence that starts with C. So of course I can assume that that is indiscernible over MB using the fact that B and C are independent. So that's why I have this fact that C prime J has the same type as C prime B. So I just missed that comment. Okay, so what did we know about the relationship between C prime and B? Well, that told us that P x B and C prime, or Q x C prime did not fork, right? That was the union that didn't fork. It was the C prime that didn't fork and C did. So P x BI, wait, why am I writing BI? I actually just mean, wait, no, that's right. BI union Q x DJ does not fork over M. But now I'm realizing that I wrote this backwards, so I apologize. This should have been B, like that. Okay, so I swapped it when I wrote it. Okay, it's like that. Cool. So on the other hand, if I is less than J, then B I dj has the same type over M as B dj minus I. This is sort of how we picked it, right? Like how do you relate to dj? You relate it in the same way that you related to the same d's, but minus some I. So, I mean, you shift down a bit to see how you relate in this case to the bigger j's. Then, so by assumption, Px b union qx, bi qx dj forks over M. Recall that we're in case one, which is that this union forks. Because our assumption was that Pxb together with any one of the dijs, di's, forks over M. So because this has the same type as that pair, this has to fork. So what we'll do is let b prime I, d prime I, as I ranges over the natural numbers, be an M indiscernible sequence. Locally based on the sequence bi di, I less than omega. Since I less than j and I prime less than j prime implies that if you look at bi dj, that has the same type over M as bi prime dj prime. And I could have written less than or equal to here. Well, it doesn't matter. Less than or equal to, whatever. And vice versa for I greater than or equal to j. We know that still P x b prime I union q x d prime j forks over M if and only if, which case was it? This was the one where I is less than j. So because the type is constant among all pairs of elements, like in the right order relations, the type of those pairs will not change when I pass to something indiscernible. So let's call this sequence I, just to give it a name. So let A star realize Px B0 union Qx D0 with A star forking independent over M with B0 and D0. So this we could do because it didn't fork. Because when I and j are equal, this union didn't fork. Then by the chain condition, there is A star star, which has the same type over M B0 D0 as A star, such that A star is independent over M with all of I, and I is M A star star indiscernible. This is what the chain condition said. You're both indiscernible and independent. But M A star star indiscernibility implies, in particular, A star star realizes Px which one was it? B0 union Q sorry, b prime 0, and these should have primes, sorry, and d prime 1, which forks over M. So you violate the chain condition. So on the one hand, the chain condition told us that we could find something which is independent from the whole sequence. But if we realized pxb0, qxd0, and you're indiscernible, then in fact you satisfy pxbi for every I and qxdi for every I. And that includes even when the i's are different. So that means you have to satisfy pxb0 and qxd1. But that union forked. So in particular, if you satisfy a0, b0, the sequence of bi's and di's is indiscernible over you, then you satisfy b0 and d1. That union forks, so you fork. But that contradicts the chain condition, which says that you're independent from the whole sequence. In particular, you should be independent from b0 and d1, and you can't if that type forks and you realize it. Okay, so that finishes case 1. So case 2 is the same. You use not the c i's, but the c prime prime i's to construct a sequence b prime I, d prime I less than omega, such that px b prime I union qx d prime I forks over M if and only if I is greater than j. So it goes the other way. Get same contradiction. And that completes the proof. Okay, so I won't give the details. It's literally the same. You just do the same copying. But the idea, which is kind of interesting, is this says that, I mean, some people have interpreted this to say that there's a kind of stability in the relationship of non-forking. Because what does stability say? Stability says that you can't somehow have one behavior going this way and another behavior going this way. You can't have like half graphs in formulas. And now we're not looking at formulas, but rather we're looking at some abstract relation, the relation of non-forking. And we're showing that that also can't have some kind of mismatch, where going one way you have non-forking and the other way you have forking. Sort of looks like non-forking. Now, what's interesting is, okay, let's suppose you look at the relationship of non-forking over the empty set between two n-tuples, okay? That's an invariant relation on n-tuples. If you're in an all if not categorical context, that's a definable relation. And under some additional assumptions, like finite rank, like super simple theories of finite rank, you can prove that that relation is stable. And this has motivated some very important conjectures in simplicity theory, which are still open. Namely, there's something called the stable forking conjecture, which says that whenever you fork, it should somehow come from a stable formula. And that really comes from this fact that you see something that looks like stability in the relationship of when elements can fork with one another. Okay, but that's sort of a tangent. So that's it for what I wanted to say for simple theories. And then next time what we'll do is we'll begin with NTP2 theories, and we'll spend a week on that. Then we'll do a week on NSOP1 and then a week on NTP1. And depending on where time takes us, then we'll see what we did with the last week. Okay, are there any questions?
Nick?
Yeah.
Can you just repeat what is the conjecture? Maybe with a bit more detail.
Yeah, so there are different variants of the stable forking conjecture, but it should say that like if in any simple theory, forking is always witnessed by a stable formula. So, you know, like what does it mean to fork? It means that you imply some formula, phi x b, such that phi x b implies a finite disjunction of formulas that divide. But okay, in simple theories, forking and dividing are the same. So what it means is that if the type of A over B divides, there's a formula phi xb that divides in such a way that phi xy is stable. So you have a stable formula that does the dividing. And of course, this is true in basically every example we know. If you look at, I don't know, ACFA or the random graph. I mean, in the random graph, forking comes from equalities. In ACFA, it comes from algebraic relations that hold between some number of iterates of the automorphism. These are quantifier free and hence stable. There are lots of things like that.
Okay, thanks.
Okay. Great. Okay. Well, enjoy your Monday, and I will see you all Wednesday morning.